What is cross-linking in polymers and composites? Imagine building a web where each strand is connected to others, creating a strong, stable network. That's similar to what happens during cross-linking in polymers and composites. In simple terms, cross-linking is when individual polymer chains are linked together through chemical bonds. These bonds are usually covalent or ionic, which are much stronger than the usual forces holding the chains together. When these bonds form, they create a three-dimensional network that changes how the material behaves. Most polymers start as long, flexible chains held together by weak forces like van der Waals interactions or hydrogen bonds. These weak forces allow the chains to slide past each other when heated, making the material easy to reshape or melt. But when cross-linking occurs, these chains are connected by stronger bonds, which restricts their movement. This process turns a thermoplastic into a thermosetting material. The amount of cross-linking directly affects the properties of the material. More cross-links mean the polymer becomes stronger and more durable. It can withstand higher stresses and resist deformation better. It also becomes more resistant to heat because the network structure prevents the chains from moving freely when heated. This means cross-linked polymers do not melt like linear ones do. Chemically, cross-linked polymers are less soluble in solvents. The network structure blocks solvents from penetrating and breaking apart the chains. This makes them useful in environments where chemical resistance is needed. In composites, cross-linking helps hold the polymer matrix tightly around reinforcing fibers or fillers. This bonding improves the overall strength and stability of the composite material. Such materials are used in many mechanical engineering applications where high loads, temperature changes, and chemical exposure are common. Practical examples include rubber tires, which undergo vulcanization, a form of cross-linking that makes them elastic and tough. Protective coatings and paints also use cross-linked polymers to resist chemicals and wear. Medical devices benefit from the stability and biocompatibility of cross-linked materials. Electrical insulators and solar panels relying on the thermal and mechanical stability that cross-linking provides. Understanding how cross-linking works helps engineers design better materials. By controlling the degree of cross-linking, they can create polymers and composites with the right balance of strength, flexibility, and resistance for specific uses. This process is a key part of material science and helps develop the durable, high-performance materials used across industries.